Okay, good morning. Before the class, I first should announce for some people, some students, they still did not pick up the midterm exam. After class, if you ask any rechecking, I also brought it here. So you can, after class, if you did not get your midterm back, you should check this, the last part. Okay. Another thing is, before the spring break, I actually announced we will have the second assignment. I think I published that one on Sunday. I also asked TA to announce it in Piazza. Hopefully you will have time to go through this. I think the due date, of course, is still one session before the second midterm exam. But I hope you can start early. You can look at this. Some questions are very straightforward. Usually, if you look at the big question, the first part is somehow review or summarize what we have learned. But the second one usually is somewhat tricky. That means the second one, you really need to spend some effort reading papers, have some thinking. It's like a mini research project. Okay. Actually, anyone, if you really do well, you extend it substantially, it could be a good course project, right? But I just want you to answer in a very brief way. Okay. So you probably can look at both first part and second part of the question and try to answer it well. Okay. Another thing is for the finer project, some students discussed with me, they discussed with me, said they originally at the end of the fourth week, when you propose something, you may not find a very good project. After these many weeks, you want to have some change. That's possible. Okay, you can discuss with TA, discuss with me, because our final evaluation is based on the final submitted report. That means the final report, the quality, is not based on the quality of your pre-proposal. Okay? So that means the end of the fourth week, that checking, is just trying to help you to think earlier to get out those papers, topics much earlier. Okay? But the final due of the evaluation is really based on your final submission. Okay? So if you have any questions, especially you want to discuss with me, try your best to use my office hours, because other time you may not find me, I could be busy with other research projects. You better use my office hour very wisely, okay? So another finer thing is our final course project presentation. The midterm exam is fixed date, is April 28th. After that, we will have a few, we have only one class slot. And whether we will take this class slot or we will change to other days is really based on our class consensus. That means if everybody, when you sign up, you prefer a later date, then we probably will not need to have May 3rd as the first presentation. We may get it into May 4th or May 5th as the first presentation. Okay. But make sure you get things done. We have very tight deadline. You make sure you get things done on time. Okay. So that's a time I should warn everybody. After the midterm, basically, is just your final project presentation. Okay. So that's about the course. So we will continue our discussion on our truth finding. Okay. Last time we discussed truth finding, I give you mainly two algorithms. One is truth finder, one is latent topic model, latent truth model, or LTM. Okay. This one actually is still real. You can see the city is really by the side of the mountain. Actually, this is the one I took from the, there's a very, very tall mountain. They have a Jesus Christ, the huge statue. You probably see that's a landmark of the city. Really get on top of this mountain. If you look at the very end, that's the part is the people can take photos on the corner. Okay, so that's a corner. You can take the ocean, the mountain, and the city. Okay. We will discuss the very last session for this one is GTM. GTM is a Gaussian truth model for finding truth among numerical data. Okay. Actually, that's the same PhD student, Bo Zhao, when he finally finished his PhD. Besides his latent truth model, he developed another model called Gaussian truth model. Okay. The Gaussian truth model, the general idea is, remember, we handle true or not true is based on yes or no Boolean answer. For example, whether this person is the author of the book, or whether this person is the director of the movie. Okay? So that's yes or no Boolean. But in many cases, they want to give a quantitative answer. For example, they may say how high the Mount Everest is, okay? Or what's the population of New York, okay? New York City. So those are the numeric data. They want you to give me a number. Okay? But remember, number actually is hard to make it very consistent because Boolean, you have only two values, yes or no. But number, you have almost unlimited possibilities you give a number. Okay? So it seems a little trickier to give the correct number. If people give different numbers, what should be the truth? Okay, so that's the one answer about this problem. Let's look at the example. The example is very true. You can see that's a table. Okay, NYC means New York City. Okay, that's Urbana. Okay, suppose you want to know what is population of New York City, what is population of Urbana. Okay, then you check the web. They give different answers. Okay. Of course, this one is sometime he checked it, he put it down there. Now, of course, it could be different. Okay, you can see the freebase give something like 8 million plus 346 something. Wikipedia give a different answer, and U.S. Census gives another answer, and some bad source give you a rather different answer. Okay, the problem becomes with this. With these, which one do you really believe? Okay, because they are different numbers. Okay, and if you look at the Urbana population, it could be even strange because this best source only give about 1,000 people. Okay, so obviously you know you have the common sense. You say this best source is ridiculous. Okay, but how do you know that? That means if you do not know you came from Mars, you just look at this. You say, I actually have no idea which one is telling the truth. How can we, without anybody trained, okay, without any real golden fact can be presented, who you really trust, which one you really believe? Okay, that means whether you want to output rather than their average. Okay, the best case is the average. You probably can see the worst case because if you take a freebase average with best source, you get Urbana is something like 20,000, but you please nobody because you can see you definitely average is not right, not the answer. The answer actually should give a very precise one, but it should be likely the true one, right? So that, for example, you say how high the Mount Everest, you definitely don't want to give an average because the average you basically distort the real fact, right? Then the problem is, can you develop an algorithm which can give you, without anybody trained, can give you the correct answer? Okay. So, of course, the quality of the source could be different. For example, we may assume U.S. Census is better, more trustable than Wikipedia. Wikipedia is more trustable than Freebase. Freebase is more trustable than bad source. But how do you know that? Okay, that means that you cannot blindly believe for example, U.S. Census. Actually, the U.S. Census could be, the statistic was done 10 years ago. Okay, but Wikipedia maybe, published a very updated number, right? So that's a reason you actually have to do good reasoning to find what is the quality of the source. Okay. Another thing is normalization. Okay. Normalization means you actually, it's like New York City is so big population like this. Okay. If you say I got a 1,000 population miscounted or 10,000, probably doesn't really matter that much. That means if your error is 10,000 but total is around 10 million, probably you're still happy, right? Because the error is within 1% or less. Okay. But if you say Urbana, you're off more than 10,000, you could be completely wrong, right? So that means there's a normalization problem we have to think. The third one is outlier problem. Like we clearly see this Urbana only 1,000 is outlier. The outlier, likely you have to remove them before you judge it. But you have to judge why and which one is really outlier, right? So that's the one he basically say, we have to be very careful. We cannot just say, get a median, get average, or everything. We do not do careful analysis, okay? So actually the one, if we think about this, we know if you get a lot of statistics, Gaussian is a very good, one. You really want to think about anything if you do not know. You get lots of different numbers. The Gaussian could be a very good guidance, okay? So that means you may think about something like a median, something like a most frequent value, but you actually want to use some kind of truth-finding algorithm instead of just to say most frequent one is a winner, okay? Or the median is a winner, or mean is a winner. Okay? But the outlier, actually, to some extent, you should be able to justify earlier. That means before you apply truth-finding, if you can actually compute and identify outliers, you kick out those outliers, it will help you a lot in the analysis. Okay. So outlier usually, if you use an absolute error, it's not good. For example, you say New York City, you are 10,000 more or 10,000 less. That's absolute one. Actually, it's not anything important. But a relative error or using Gaussian confidence interval will be much more reliable, right? So then he worked out an algorithm to do some pre-processing to remove some outlier. The outlier, usually you can do it using Gaussian confidence interval or using some relative error, okay? But the remaining one, you really have to do something more seriously, okay? So the more seriously, what he did essentially is using this probability graphic model still. The general philosophy is you know the source, and also you know the facts, the claims, okay? But you do not know the other things. The other thing is hidden, so you draw these graph basically saying is there's a Gaussian, mu, and a standard deviation, okay? And based on this, you can work out any Gaussian formula, right? But that's the initial one, you can give one, but then you actually may have the quality of the sources putting into consideration. Overall, both this Gaussian and the quality of sources will play the role to give you the real claims, okay? So that's just general philosophy, okay? With this philosophy, actually, you can first just set it, the mu is 0, the standard deviation is 1, and your variance is 1. You can actually do some calculation, okay? But the general philosophy is still the same as a typical probability graphic model is compute the likelihood using this map inference, try to find which one give you the best value. And then use either Gibbs sampling or expectation maximization. You turn this one into loop, you finally will get the result. Okay. But since we did not systematically introduce this probability graphic model, I will not get into detail on this, but you should know is essentially is you compute the likelihood and try to find the best value. But to get this, you need an inference algorithm like Gibbs sampling expectation maximization algorithm. Okay. The expectation regularization algorithm, I just give you the formula he used or he worked out is this. Okay. He, besides putting the typical Gaussian, to do the computation to calculate the average of this mu, he actually put some regularizations. Essentially, is putting something can smooth the error. Okay, and with this, he compute the mu, compute the variance, and put them into loop. Essentially, it's kind of EM algorithm. Okay, but I will give you the result you probably can see because of the very detailed the formula how to derive this is in the paper, but basically it's the probability graphic model based on the plate graph. Okay, so you probably can see he really used this to calculate the population of the cities. You probably see the population of city. He used lots of sources, 2,000 sources, 1,000 city year pairs, because different year have different claims on the population, and 4,000 claims. Okay, and for biography, like the date of birth and date of death. Okay, so he also tried to calculate find the truth, and you probably see this claim on the biography. The claim for Wikipedia is over 1 million claims because Wiki contains lots of people, right? So, but the interesting thing is he made one assumption, says the Wikipedia keeps editing. He will implicitly treat the very last value as the truth value, okay? Because, of course, it could be wrong, but in many cases, when you get a new version, like when the people died or when the birth date or the population of a city, likely the last edited version could be the right one. Okay, that's a general assumption. Of course, occasionally some people edit it, take the right one and turn to the wrong one. But the majority of people, they do have some quality control, right? People actually read it. So to that extent, he just assumed the very last one is the truth. Okay, then you probably can see he actually using his truth finding algorithm, comparing with many other, including his own LTM. LTM is for Boolean, justify which one is true or false. It's just a binary. But his GTM is based on the Gaussian distribution. Okay, and you probably can see these two are two different ways to compute the error. One called mean absolute error, written as MAE. The other is root mean square error, written as RMSE. Okay, then you can see this is the population of the city, and his GTM algorithm, the error, no matter you use MAE or you use RMSE, is the smallest one compared to the others. Okay, that simply says, actually using this Gaussian truth model, you will get a better truth rather than just take average. You think about a birth date, you take an average of birth date, it does not make sense, right? But you find the right one. You give that's a birth date of Obama or something, then probably you get the real truth instead of trying to give one which is please nobody, right? The same as bio data and population data, you can see in all those cases, his method on Gaussian truth model give you the best value. Okay, comparing to the others, for example, he compared with his LTM. LTM still make more errors. But in many cases, this choose finder sometimes could be very wrong. Right? And that's the general philosophy of the paper. I should say is this one. This one is the one I took at the same place. I took the one you see is really big. You have to lay down almost shoot up because it's so close. Right? But one thing I probably can show you is you perceive on the top of these these two are the very big one. I get people hanging that you can climb up. You can watch the statue. Okay, so this one now you can see it looks so small, so tiny. Actually, you can hang a very, very thick those string. The rope you can climb up. Okay, so it's a really big one. And I probably should say this is a very interesting, very dynamic domain. I had a previous PhD student, Jing Gao. She now is associate professor in University of Buffalo. Her recently accepted NSF proposal is on this truth finding. Okay, actually, next month, early May, she's going to give a tutorial on integrating truth finding and crowdsourcing, because crowdsourcing has lots of different people give the answers, but the answer could be right, could be wrong. Okay, and there's no absolute judge. You have to use algorithm to justify which answer is right. So to that extent, crowdsourcing and truth finding are very much related. She gave a very nice overview tutorial in SIME Data Mining Conference in May in Florida. Actually, she says, because I was a co-author of the tutorial, she says based on the conference requirement, I have to go there to present some part as well, which actually overlap with our final project presentation. That's the reason we have to work out. I have to fly down there and come back. Then we will do the final project report. My flight time is May 6th to 8th. So when you try to plan your final project, likely these 3 days or 2.5 days we have to avoid. The other days it's okay, we can do the presentation. Okay. So these are a bunch of very interesting papers. Some I do not really have time to lecture. For example, Luna Dong, she did many very important work on truth finding. These two papers are quite highly cited papers. One actually on the copy detection. The general philosophy is, what about you got a fourth thing, but there are many other people copied this. Just thinking about, suppose Barnes Noble got something wrong. Okay, the author could be wrong. But there are many small vendors. They do not do their own data input. They just blindly copy Barnes Noble thing. Then the error will propagate. Finally, if you blindly use truth finder or majority voting, you will get it very wrong. Just because Barnes Noble did it wrong, everybody did it wrong. Not everybody. There are somebody, they did an independent one. So with copying, you have to detect that these are the copycats. Okay? Those copycats is somehow their weight or their trustability has to be reduced based on where they copy from. Okay. Then the copycats, their announcement will be discounted. Okay. So that's her algorithm on this. She actually, last Friday, I also met her because now she's in the Google research part. They are doing a very interesting thing. They just got a paper accepted by W, like Jia Lu. But I got their paper. I just say, no, unfortunately, it's a very nice paper. We don't have time to lecture it. But maybe next year, I will take the Google paper to be part of our course. Okay. But there are many other very interesting papers. Okay. So that one, we finish our truth finding. I just give you a very brief introduction, but it's a very nice topic. There are lots of papers on this, but I think that our group actually did some milestone work, and these papers are very popularly cited. Okay. Now, I'm going to give you another very interesting topic, is stream data mining. Okay. Since we said that this data mining can mine almost any kind of data, a very important data is data stream. Even you look at the picture here, you look at the flow of the clouds or air. These are data streams. If you do the real-time, weather forecasting, you are dealing with data streams, is for sure, right? So since I'm discussing data stream, I took all these streams. Okay, this one, if you look at these stream actually on top, these are the ice and snow. Actually, this is on the top of Yellowstone National Park. Okay, I visited Yellowstone because I give a talk in Montana State University, but that's actually before the ending of the spring semester is early May. It is still very cold there. You probably can see the mountains still have lots of snow covered. Okay. So let's discuss about a data stream. I should take those animation out, okay, because sometimes it really bothers me to give all these. The data stream actually is, we see all the time. It has been very, very popular in the since year 2000, okay, because after people are working with solid data like database data in structured records, then people realize there are two things you really want to work. One is unstructured data, like these text or these unstructured data. Another one is data stream, dynamic data. Dynamic data means the data come in like water. You think about, there are many people at home now, they have the video camera, you can watch, you log on the internet, you can even watch your home, what's happening in the home. That means the video actually took those images and pictures from your home, they put it on the internet. Then in the office, you want to see what's happening at home, you can click a button, you can watch the video camera. The video camera gives you the data, actually data stream data. Because they are continuous, ordered, they dynamic changing, they are in huge volume, and also if you want to process them, they come and go very fast. Okay, that's very different from traditional database system. You are dealing with finite, persistent data. That means you process the data today or tomorrow. Essentially, they are the same. Okay, but that's different. In data stream, it's very different. The interesting thing is now many people are thinking even the huge data like on the web, when you process it, you better treat them like data streams. You think about it like a Google. They scan the web, they get all things. They want only have one scan because of the web, the data is so huge. When you do indexing, you don't want to say I scanned it 3 times on the whole web, I built an index. They want to scan it and build an index. They never have to go back again because otherwise it's too costly. Okay. So there are many, many such things. They want to adopt data stream algorithm as well. Data stream algorithm most important from the algorithm-wise, most important thing is random access is expensive. And a single scan algorithm is a must. So-called single scan is when the data come, you want to do everything. You just assume you will never see this piece of data again. You will do all the needed processing, let the data go, then that's it. You will never see this one again. Okay. So that's what we call single scan algorithm. And it's very important because with a so huge amount of data, there are many algorithms, they also just want single scan. Okay. So to that extent, there are many, many data processing algorithms. They like this data stream algorithm because even they say, now I have huge disks. I can store anything you want. They still want data stream algorithm just because turning back the disk and reading and indexing it and try to find the place again is very expensive. Okay, so that's why for data mining, you have to think about it, not just mine the regular data, you want to mine stream data. Okay. Then you probably can see there are many, many applications in stream data, using stream data, like a telecommunication. Okay, like a business, you get a credit card transactions, and people actually want to bet on the different price or something. They want like the data stream algorithm as well, because you don't want to store them and index them. You want to make a real-time commitment. Okay. Network monitoring, traffic, financial like stocks, like engineering process, like a power supply, manufacturing, chemical experiments, almost anything you want to think is data stream. And a sensor, surveillance, that's very, very useful, right? We know the sensor, what you do is you really want to do real-time processing, okay? And security monitoring, web logs, and web click streams, okay? That's all data stream methods. Even for the very massive data sets, they want to use data stream algorithm as well, okay? Then we can do the comparison side by side. This one was done by Rajiv Modwani. He did a conference tutorial in 2004 in POTS conference. He was a professor in Stanford University. And what he did was he did line by line to do the comparison for every aspects, okay? Like when you deal with large databases, you're dealing with persistent relations, but data stream deal with transient streams, okay? You may do ad hoc queries, but the other one doing continuous query. What is continuous query? Continuous query means you put a query in front of these data streams. The stream coming, your query keeps, it's more like a watchdog, okay? You're thinking about it. If you think there should be an alarm, like a fire or like a theft or explosion or something, you want to watch, what you do is you put a query down there. The query keeps watching the situation. The data stream keeps going. The query is the same. Say, something like watching explosion or a theft or something unusual. Okay. That query is exactly the same query all the time. Okay. But the data flowing in, just the query just checking the data. That's why it's the same query, it's continuous query. Okay, it's the query all the time, it's there. And you do not do random access, you do sequential access, but you have a bounded memory. It simply says your main memory is limited. You have, 500 megabytes, that's all your work. You can only process this using this memory. And historical data is important because you want to compare with the history. If the history, this part is very quiet, now it becomes very noisy or very dynamic, you may guess what's happening, right? And you need a real time. You have multi-gigabytes arrival rate. Actually, you probably see if you watch the video, it's really multi-gigabytes. Even now, you do the video, most are doing streaming, right? And data are at a fine granularity. That means the data can be on every bit, like you watch the video, stream video. It's very detailed, okay? But you want to do the summary, to do the final processing at a very high level. You say, now there's something unusual, okay? Rather than you look at every bit, you actually have a global view. This one is not like a usual case, right? So this is very useful. Then we look at the data stream, the processing. Usually the architecture, it looks like this. You get multiple streams streaming into your processor, your data stream processing system. Okay. You have a scratch space, most on the main memory space. You store something like summary or a usual case or background or something. Of course, you can use disk, but you know the disk has a delay, right? So you link to a disk, you may not want to use disk that often because data stream, the response time, the analyzed response time, has to be usually in the milliseconds, right? And what you see is you are posing continuous queries, like watchdog queries. The results, like it's normal or not abnormal or something, they are going to streaming back. Okay? The result is streaming as well, but the continuous query is just a single one or a bunch. Okay? Just keep watching it. Okay? So the problem is you do data mining, now you only can scan the whole data once, and you have to do the real-time response. How can we do that? Okay. So there are lots of problems. Some challenge is on query processing. We are not going to discuss more. If you really want this, you have to take a database course like Aditya or Kevin may give you more detail on the stream query processing. I'm not going to give you the details, but I should say is usually the query could be very complex. For example, you just say, I say there's something unusual. To justify this something, unusual, the query itself is very complicated. It's not just like this value is bigger than 3, okay? But you actually have a very sophisticated evaluation of the whole situation. So it's a continuous, it's complex, and another thing is multi-level, multi-dimension analysis. Because you think about it, if you can watch every bit, every pixel in your big frame, and the frame actually come down like every minute, every second may have like 20 frames coming in. So you cannot down to the analysis of every pixel. You actually have to go a little higher level. Data is at a low level. Your analysis and conclusion should be at a high level, and you have to watch many dimensions. So it's a very tricky. But we are going mainly thinking about the data mining tasks, because the query processing itself is very tricky. But the query usually require very precise things, like how many things happen. You have to count every one. So the query sometimes, even using a query, in many cases, comparing to the data mining, the data query and data mining query, if you think this database query sometimes in stream, it's more difficult. Just give a simple example. Okay? If you want to join two relations, okay, how could you join the two relations if these two relations come at a different time? Remember, you want to join these two guys, the same name, you want to join them together? This relation, this person already gone, long gone. This one says, I haven't come yet. How could you make a join? Okay. That simply says the simplest one, like a join, is almost impossible in data streams, right? Because the other one is already gone from your main memory. The join partner is still not arriving yet, right? So they are not completely synchronized. So there are many very, very hard problems for database people to handle. Okay? But data mining sometimes is a little easier because you are not require something very precise. You want something like a summary or some kind of patterns or outliers. So to some extent, it's like a sorting and a join. It's almost impossible in data streams for database people. But for data mining, we are not doing this. Okay? Of course, if they give us something, you say you have to first join before you can do anything, then we're dead. Okay? So we just could not do it. But in many cases, the data mining can give you something quite interesting, but you still can do it. Okay? One is a multi-dimensional online analytics. The second one is pattern mining. The third one is classification. The fourth one is clustering. And the fifth one is anomaly analysis. Of course, with a limited time, I will not be able to cover all of them. But I will give you the general philosophy, doing a lot of hand waving, but give you the real example how these things can be done in data mining. Okay. So the data mining, the most important thing is the data actually comes at a low level, okay, and also maybe a very high dimensional. But what you need to draw the conclusion at a high level, maybe low dimension. You can present to the people can understand. Okay? So the first thing I want to discuss is stream data cube and stream OLAP. Okay? So that's the first one. This one actually is I just go down a little for the same picture. You see the water rolling down. That's the one I took the picture on the top. Now I took the picture on the side. These are also the Yellowstone snow. You probably can see the snow is pretty thick. And the water actually dropped down is really, really deep. It's a very, very deep part. And in Yellowstone, you probably see there are lots of very beautiful scenery as well. Okay. Now let's look at stream data cube and a multi-dimensional OLAP analysis. Actually, this work was done by working together with one student in this class when the first semester came here, 2001. Okay, there was one student called Yixin Chen. Because I came, he was not my student. He just took the course, but he did a really great work on this multi-dimensional stream data cube, and the paper was cited very popularly. And after graduation, he joined Washington University in St. Louis, very close. Actually, I met him last month in St. Louis. And he is full professor already, promoted very quick because he did it really well. Another impressive thing is he joined WashU. He got a Microsoft Young Faculty Fellow, which every year in the whole country, or probably in the whole world, there's only 5 people across all the disciplines. And most of the people got this one is a professor in Harvard or Stanford. And he was in WashU, he got it. Okay, it's very impressive. So now actually I talked to him. He said maybe he already got tenure, get a full professor. He probably even want to think about moving to another university. I said, which university interested you? He said at least one professor in Harvard chatting with him. Okay, simply said he's really great. And he got the most cited paper actually in this course. Okay. And I probably should give you this interesting thing is web clickstream. If you think about this, suppose I want to give you this query. I want to have a watchdog to find something interesting on the web click. Okay, the web click. Suppose you want to get an answer like this: average click traffic in North American sports in the last 15 minutes is 40% higher than that in the last 24 hours. Okay. Suppose you want to get such a summary. Then we look at how challenging it could be. Okay. The first thing is North America. Remember, when you click, even you were in Google or you were in Yahoo, okay, North America is very big. Okay, so you have to summarize many, many things. Okay. Then sports is also a very big domain. They cover so many things, right? Last 15 minutes, remember, if you think you're analyzing clicking streams, 15 minutes is a very long time. Your data will not be able to store there for 15 minutes. Okay, they are looking for sub-seconds, milliseconds instead of 15 minutes. And the comparison is 40% higher than last 24 hours. Last 24 hours is long gone, right? If you want to just think about your watchdog, can finally give you this answer, you need to think of it, you need something magic to make it, right? Okay. Now we look at the power consumption. Suppose you were in Chicago, you were watching the Illinois, some power station on the power consumption. Suppose you want to find a pattern like this. Average hourly power consumption surged up 30% for manufacturing companies in Chicago in the last 2 hours today than that of the same day a week ago. You think you can do it? That's almost equally challenging. You think about it, you get a surge up 30%, you get a manufacturing company in Chicago. They actually have different sockets, but there are so many different manufacturing companies. Okay, 2 hours a week ago, all these things becomes almost impossible. You think it's very simple query, but if you want to find such pattern, you do need some effort, some special design. Okay. So now I will discuss with you what is the design. Like Yi-Shin, Chen, and me, we in the class we discussed rounds and rounds of work out this design. We call it stream data cube. Okay. Because at that time, why he was interested in this? Because that time Stanford was working on stream data query. You look at Modwani, Jennifer Whittam, Hector, they all go crazy, went crazy working on query processing data streams. They say it's very hard. Okay. But we say we are doing data mining. We are now working the same game, try to do join or sort, which they already shown is impossible. But we say we can do something magic, which could be possible. That's why we get into the stream data cube. Okay. The stream data cube, we have 3 critical things in the design. One called a tiered time frame, another called critical layer, the third one called partial materialization of stream cubes. I'll explain one by one on this design. The first design we call tiered time frame means the time, if you say you want to register second, remember if you say 2 weeks ago, the second there will be so many, right? And it's impossible, you say, I register every second activity for 10 years. You don't have main memory, don't even have a disk to hold this. Okay. But if we do tiered time frame, that means at the most recent, we can register every second. Okay. Then we get a minute. After a minute, we say we just need to see the regularity. The granularity is just a minute now. Like after 10 days, we say we're probably only interested in the day level, okay, rather than second level. Then if you get a century, probably only interested in year level. I don't even interested in which second happened. Okay. Actually, there is a very interesting thing. When I start saying this, I probably first show you our tiered time frame, okay, like this. Okay. That means suppose we want to know every 15 seconds. Of course, it can be even 15 minutes. It could be even more fine. Okay. We say, suppose you have 4 slots. Every slot you can sum up. Sum or average or count, whatever. You get it. Is 15 minutes a slot. Okay. Then the last hour, you need 4 slots to hold things. Right? 4 slots, that means maybe 4 bytes or 4 bytes. Okay, you can hold this thing. Then you can see after passing an hour, you say now I'm only registered at the hour level. Now I need 24 hours. Then after 24 hours, I only interested in day level. I give you 31 days. Then after day, I only need a month. Every month level, I register every month. Okay. I can design my tiered time frame like this. Then even you say, I need 10 years data. Like this year is better or far. I save more energy than 10 years ago. Can you do it? You still can do it. Because how many slots you need? Remember, after 12 months, it's just year level. Okay, suppose a year level. Then what do you need? Just 10 more slots, you get 10 years, right? Okay. Of course, you may say, now you lose all the granularity. 10 years ago, you would not be able to know every minute. Why you want to know it? Okay, the question. Actually, once you say that, I probably still remember Ronald Reagan, okay, because his wife just passed away very recently. I remember when I watched TV, the time he almost going to retire, okay. Then some journalists start asking him, said he was lying, said he could not remember, the Iran Contra. That means what he discussed with people about during the lunch. He was discussing with one diplomat, said something about Iran, and he said he could not remember. Okay. Then the journalist just challenging him said, you were lying. Okay, you could not remember. Then he said, that's already 8 years ago. He said, could you remember the 8 years ago during the lunchtime? What do you talk about? I said, my memory is limited. I could not remember what exactly I talked 8 years ago in the lunch. But I bet you cannot remember either. Okay, so that everybody was laughing. To some extent, what he said is truth, right? You can say he was lying, but he said, I really could not remember. And because that's a stream memory, right? You can remember granularity in the year level, but you may not remember the lunchtime exactly what you talked. Okay. That's the same thing. Okay. Probably you don't need in most stream analysis, right? Why you need a particular minute 10 years ago, right? So that's why we sacrifice the granularity or the finest granularity. But we actually use very limited memory. We can handle those things. Okay. So this tiered time window can be in, this one we call a natural tiered time window. Another tiered time window we call logarithmic tiered time window. Logarithmic means this is t. T could be a second. But immediately after that, you get a 2t, you get 4t, you get 8, 16. You keep doubling. Okay, that's very powerful. Okay, you don't need that many slots. Remember, 2 to the power of 100, you almost can register anything happening in the whole history of the universe, right? So you just need 100 slots. You think in that way. So that's the reason logarithmic tiered time window, you also can save a lot of things. You still can get certain granularity, and you can go back to a longer history. Another interesting thing actually was another tiered time frame. I probably did not put it in. It was a tiered time frame I co-authored with Shahrukh Agrawal at IBM Research. He developed a tiered time window which called pyramidal tiered time window. I probably think is too much. I just erase it. But it's a very nice design. Like you have like 5 slots. Okay, then you have n slots. You just mod 2 to the power n. 2 to the power n. You based on your mod number, you put into the right slot, and then the downgrade, the degrade will be going very, very decently. Okay, more decent than this one. This is just natural. This is too radical. It goes back too quick. And he wants to slow it down, but with a decent registration of enough granularity. And he proposed a pyramidal tiered time frame. I just did not put it in. Okay. So now let's look at the second one called critical layer. Critical layer means when you want to analyze like power consumption. The power they come in could be in the sub-second. Okay. That means the real granularity can be sub-second. But unless somebody really, like an electrician, really want to know sub-second what happened, most people do not care sub-seconds. Maybe what you care could be, say, quarter, like every 15 minutes what's happening. So your minimum interest layer is normal user. You're interested in, like I do analytics for the power. I go to every quarter, maybe it's good enough. So the minimum interest layer could be quarter. Okay. Then observation layer could be on the very top, like you watch the whole data frame. The minimum interest layer could be even higher. Just give you an example. Okay. Suppose you were working for Illinois Power. I do not know whether there's such company called Illinois Power. But suppose you watch the whole Illinois. Okay. Do you want to watch every household? It's impossible, and it's not necessary. So your minimum layer could be at the county layer, because Illinois has many counties. You watch every county, say this county, now the power consumption is what? Probably is good enough. That's we call observation layer. Okay. Of course, you can drill down. You can drill down to every household if needed. Okay. That means you watch at the observation layer, and occasionally you need to drill down to the minimum interest layer. Maybe minimum interest layer could be a city block or could be a house, but you don't want to drill down to every fridge or every light bulb. It's not necessary, right? Another third thing is about a partial materialization of stream cube. Partial materialization means the stream, you build up the cube, there are many, many possibilities generated and many combinations. You cannot materialize or pre-compute everything. You only pre-compute some partial thing. Then when people need it, you do a little more computation, you can get things you need. Okay. So let's just give you something. This is the typical data cube. I assume if you ever took CS412 or even some database course, you probably should know data cube. Okay. Data cube's general idea is this. The real data is a very low level. You get multi-dimensions, like a time, item, location, supplier. You can chop up any dimension, any level. You can go up to have aggregated cube. The highest aggregation is single point, like a sum, like a total power consumption. Okay. But then you can go down like a power consumption based on location, based on supplier, based on item, based on time. You can do that. Okay. Then you can go down even lower. Okay. So that's the case. And for this, we already showed you the theory time frame. Okay. Now we show the minimum interest layer. Okay. The minimum interest layer is this. This is the lowest layer. This could be the real power consumption, the real power flow in every meter. You get into this. Okay. Then you may only interest in minute layer instead of second. You may interest in URL group or user group instead of every individual user, every individual URL. Okay. So that's the drill down you are going to drill to the M layer, minimum interest layer. But as a normal observer, you are observing at a very high layer we call observation deck. Right? So between this observation layer and minimum interest layer, you can construct a data cube. A cube can help you to drill down to any level, any dimension combination you like. Okay. But you are not going to pre-compute every cuboid of this one. You only compute something needed. Okay. So this will help you to do OLAP operation. That means you can drill down, you can drill up, you can do slicing and dicing, you can do pivoting. So you can play anything like other data cube. Okay. But this one, the most important thing here is you can only afford partial materialization. What is partial materialization? That means I just give you just this picture to show you what you want to materialize. Okay. Suppose this one is the lowest layer, minimum interest layer you have data stored. Okay. This storage could be in theory time frame in the main memory, or they can even refer something lower on the disk when needed. But most time, you play the stream in the main memory. Okay. Then, how do you want to summarize? You don't want to summarize every cuboid because it's too big. For example, you think about it, you get 10 dimensions, you get 5 levels, you get many, many cuboids. 10 dimension means 2 to the power 10 is 1,000 cuboid. And if you count 5 levels, you get many more, right? So you don't want to compute everything. You only want to compute in a reasonably sparse way. So your memory is saved. But in the meantime, you can support people want to drill down. You can support many other operations. Just thinking about this, okay. Suppose you are the Illinois Power, you're on the observation deck. You watch the whole Illinois, how the power is fluctuating. Okay, you're at this level. Okay. Now, you may say, I drill down to county level. Originally, the county, I drill down to the city level. And I drill down to even the city block level. Okay, that's the typical way I drill down. I want to see what's happening. Like if I see this county, the power really used a lot, I want to see what's happening and look at every city or every village. If I want to do that, this is my drill down path based on location, right? Then I may even drill down based on the time. Okay, like last hour, this hour, what's doing comparison. I can drill down to some other things. I have a popular drill down path. What we need is just to take this popular drill down path, we materialize all these. Materialize means you do a lot of summary, you materialize this one, okay? Why you want to materialize? Because you don't want to compute on the fly. It's too expensive, okay? And plus, for data cube, you really do not store all the data. What you do is you only summarize to a certain level, you only keep those things. Okay? But that's very important. You think about this. Okay, suppose you were Walmart headquarters in Arkansas. I think the Walmart, the family really in Arkansas. Okay. Suppose you want to see Walmart, the current situation, okay, because you want to get the stocks and everything, want to see current gain or current sales. You may watch at the state level, okay, and then you may go down, but you also not only want to watch at the state level, but you also want to watch at the section level, like whether baby products or, women's clothes or, the food or, like a tire or a car or something. You want to watch in that way, okay. But you want to find something wrong, you want to drill down. Remember, you saved at the minimum interest level. That means you probably don't save every store, every product, every particular code. But you can never say, when I click the button, all the states, 50 states, all the baby products, every item doing online summarization. That's too expensive. That's why you need to store something, aggregate something beforehand. Okay. But why you only aggregate this popular path will be good enough? The reason is you can think about this. Okay. Suppose you say you drill down following this. I am another manager. I drill down following this path. Can you support me? Actually, you can't. Why? You can think about this. Okay. Now you drill down, follow this path, you go to A2 star C1. I do not have pre-computed cuboid to support you, but I have this one. I have A2 star C2. C2, C1 is quite close. These A2 is the same. That means I just need to summarize some cuboid in the middle. You can see, you say this one I cannot support, but this one I can support you. Okay, this is more like this. Okay, here you go to Illinois. Here you go to baby products. Okay. But these baby products is summarized at the level. Okay, if this guy wants to say you drill down Illinois, I drill down Michigan. Okay, it's fine because here I keep the low level. Okay. But if you say baby products, I already summarize all the baby products already. I don't need to see every particular baby item, right? Baby product item. That's the reason you can use this one. You just need a little roll up. You actually finish the query. That's the beauty. You don't need to start from scratch every item to do computation. That's what we call online partial materialization. Okay. And with this, we actually propose a data structure which is called H-tree structure, which was published a few years earlier. We use this structure. We show what we showed is a really power line consumption, which is a regression. And Yixin Chen, he did also, I think, the undergrad in electrical engineering. He knows the regression line, all the regression parameter very nicely. And he just shows for stream computation, you do not need to store every single point on the regression, but you only store some intermediate parameter on the regression in a very small number. You can restore the whole regression line in a very nice way. Okay, so he basically showed that one. He shows several regression computation you can done in the multi-dimensional, multi-level computation. Okay, but I will not give you the very detail. That's a data cube design. Okay, that's what we call stream data cube, which later many people have been used. I think even I know of quite a few companies, they actually are also using similar structures to do the computation on the data cube. Okay. Now I give you another very interesting stream mining method called stream frequent pattern analysis. Okay. Stream frequent pattern, I really hate those clicks. I just click everything first. Okay. Stream pattern one, the very interesting thing is this. Okay. Everybody wants to find a frequent pattern, including frequent single items. But you have very limited space to store them. Okay. And what you want to get is, instead of precise answer on the frequent pattern, you may just want to get an approximate answer. Okay. The first thing people may actually wonder, now you have a very big memory, very big main memory, why you want to get a pattern, you still just want to get approximate pattern rather than precise pattern. Okay. I just give you a single example. Just thinking about a router and the router routes. Okay. You think about it. You click a button on the internet, you request things from, say, Google. Okay. Actually, you are not directly linked to the Google. If anybody knows, is you link to a very local one, the router link to another one. There is a long path. Of course, you do not sense that. You click a button within a second, you got the answer. You think it's really great. Actually, there are lots of very complicated things going underneath. That's why the Google side, like Mingji told me, their response time, the maximum bound is 100 milliseconds. You go down there, they will not allow you to deliver the product. The reason is, if you take 1 second, then think about a router request and going back, there are many, many other things. It will take time as well. Then finally, the user will think, my computer is hard there. Okay, they will not use your service anymore. So that's the reason. But how many routers? The router, can they register all the requests? There are so many. Okay, so that's the reason they want to find pattern. You think it's a small number. Remember, every router still have a limited memory, and it's impossible to handle data streams using like terabytes memory to try to register every possible request, right? So that's why precise frequent pattern mining in data stream may not be realistic. You have to think about approximate patterns. Okay. But approximate pattern likely will give you the error. That means sometime may be overcounted, sometime may be undercounted. But if you can guarantee the error is less than, say, 1%, you probably will be very happy, right? So who cares? Right? If my error, I give you this one, say this one is frequent, the count is 99. So the real count may be 98. So who cares, right? You say 1% error, I definitely will tolerate. So the problem becomes you can only get an approximate answer, but you want to get a good approximation. Okay, that's the key. Okay. Then there are lots of very interesting proposals in the early year 2000. That's why I'm introducing you. One is Manku and Modwani. Their algorithm called lossy counting algorithm. Okay. In the same paper in 2002, they actually proposed two. I only introduced one, just give you a sample. Okay. Lossy counting, and Modwani really generated lots of data stream algorithm. We're going to introduce quite a few. Actually, just you know or you do not know, Modwani actually passed away around the year 2006 or 7, I forgot. Actually, it was really accidental because, remember last time I told you the Google's co-founder is Brian and Paige. Brian actually was his advisor. We put as a Modwani. The real advisor was Jeff Arman. Modwani, of course, got surprised the Google co-founder quite a lot, and he was very, very famous, very smart one. But he got Google got a wing. He got a really big house with a swimming pool with everything. And it just happened he never swam. He could not swim at all. He got a very big swimming pool. Actually, one day they got a big party in computer science in his house. His house is really big. In Bay Area, it's quite expensive. And he actually, after the party, he was cleaning. But accidentally, everybody left. He was still cleaning. Accidentally, he fell into a swimming pool. And then that's it. The second morning, actually, the family found his body in the swimming pool. And that was a Sunday or it was a weekend. Actually, then Jennifer Widom actually announced to the whole world. Of course, I was online. Said that Modwani passed away. We were very shocked because he was very young. Okay. But he was so brilliant. I think our best theory person, Jeff Erickson, probably got a PhD from him. And he was a very big theoretician, one with a randomized algorithm with a book. And his stream data mining, we got lots of papers. I actually will show you this algorithm and then the later algorithm on his one. Just unfortunate, he should learn to swim much earlier, right? Okay, so we just finished this. We are going to continue our stream data mining next lecture, okay? So anybody did not pick up the midterm exam, you should check it here. Okay, thank you.
GTM, the truth finding.
Yes, yes.
So I wonder why we just use the highest quality source as a truth, then we don't need the truth.
Because you do not know which one is true, right?